there. Are you able to hear?
I'm not able to hear. I'm okay with the audio. I think it's fine for me.
I don't know why it's coming. Let me hang up.
Audio is quite okay.
Very clear to me.
Audio is very clear to me also.
The thing is, for me, it's coming back.
Your own voice.
Is it my?
Have you got two devices operating at the same time?
I think I.
Yeah, that will be a problem. One of the devices you have to.
No, if you switch off the audio on one,
yes,
both the microphones.
One of the audio you
in fact, I've shut off the other computer anyway now.
Okay.
But still, I'm getting echo.
You made the audio completely zero in one of the devices?
No, this all iPhone is closed. Shut off. Computer is shut off. Still, I'm not sure because it's coming back actually the sound.
I see. Okay. Would you have a headphone to use? So maybe that will avoid the issue.
Pardon?
Would you have a headphone that you can use?
No, I didn't get it because doubles sound.
Because we can hear your audio quite clearly.
But sir, if I see the participants list, there are two names of Amar Garg here. So I was just wondering that twice you have using this one or something.
Well, the thing is, I've already shut it off.
In fact, there are three Amar Garg.
Yes, because I had logged in from my iPhone, then logged in from another laptop, but I put off the iPhone and also the computer off.
Maybe you haven't logged out of it, so it might still be active, the connections.
Oh.
Might have to leave the call before switching off the iPhone and the other computer.
But the sound cannot come if the computer is off. Totally.
So with your permission, we can, if required, we can remove one of them. So probably sir will be able to solve that.
Okay. Let me do that.
Yeah, maybe can you put it off from, except this one?
Yeah, I've removed the other two from the meeting now.
But it's still the echo is there on my computer.
Oh, okay.
They want me to.
You should rejoin. So you should rejoin.
Maybe I'll rejoin. That is better.
Okay.
Yes, sir.
Yeah.
Is it better now?
Well, still again, is echo. Let me see why echo is coming. Okay. We can continue.
Okay, yeah, sure.
So one more participant is shown as Amar Garg 68. So probably that also, if sir can.
Let me just.
Maybe can you shut it off? I don't know. I might have logged in a couple of times.
Oh yeah, you're right. There's a fourth one.
So
yeah. How about now?
Yeah, now the echo is not there.
Oh, wonderful. Okay. So you were brought in 4 times. I removed 3 of them.
Yeah, maybe. Yeah. Sorry for that. I didn't realize. Okay, now again. Good afternoon. again for this lecture. This is the second lecture of this lecture series. And we'll continue from where we left last time. Last week we had good response from you people, and then quite a few questions were asked. At that time I did answer some of them, but of course they might not have been so detailed answers very satisfactorily. So what I did, I just picked up the questions again and prepared better answers in detail and sent you the presentation. So what I'll do now, before we proceed further with the lecture, let me just clarify the answers to those questions which we had last week. So I'll open that presentation. Can you see my screen? Hello?
No, not yet.
Oh, is it?
No,
Oh, maybe I'll go back
maybe
to
the other.
Maybe I'm not sharing, it seems. Share. Come on.
Yes, you
Yeah.
can see.
Yes, we can see it now. Yes, sir.
It's okay?
Yeah.
Yes.
Okay, good. And you can see my video also or no?
Yes, we can see a video, but only up to the nose. So
That's the thing is I have to bring that.
yeah, that's good enough. Yeah.
Yeah, because then what happens, the view for my presentation becomes very odd.
I see. So please do it however it's comfortable to you.
So this is okay.
Yeah.
Okay, now.
Your video may not be seen by everybody depending upon the gadget which they are using. I am using a cell phone, so it doesn't matter. Your screen is visible, sir.
Okay, that's more important than looking at my face anyway. Okay, so some of the questions which I just highlighted over in this presentation are, first was how the passenger comfort improved with as well as composite structure, because I did say with the introduction of composite fuselage, they were able to increase the cabin pressure, and the question was asked, how does it get related to the comfort? And I provided some explanation, but I thought here in this presentation, I'll put a bit more explanation to make it pretty clear. Then another question was asked about alternate source of material qualification, variability in the processes and manufacturer. How do we qualify for that? Then material selection criteria. Of course, material selection criteria, anyway, I'll be talking about the details of my blending block approach diagram. Then fatigue test of aircraft, why it is needed. Are the analysis methods not sufficient? So why the point design expensive in long run? So I thought I'll just provide a bit better explanation to make it clear for you. So now what you see about this cabin pressure altitude, as you might know, but that current practice so far until this Airbus 350 and Boeing 787, the practice was to design the cabin pressure altitude equivalent to 8,000 feet. The reason being 8,000 feet, of course, what was found that still the human body can sustain for a long time at that pressure. But increasing the altitude will provide very much uncomfortable life for the passengers. So this has been historically right. In fact, the first Comet, which was a commercial jetliner, was designed with the same 8,000 feet altitude cabin pressure, which had been continuing except the Concorde. Concorde went for 6,000 feet altitude at that time, but most of the commercial jet transports have been 7,500 to 8,000 feet altitude. But with just because if they try to bring down this cabin pressure altitude, it means the differential pressure, because they are designed for a cruising outside pressure at cruising altitude, normally around 43,000 feet or 40,000 feet, depending upon the type of the jet transport. So the differential pressure will go up. That means you are overstressing the fuselage structure and reducing the fatigue life substantially, especially if it had been a metal structure. And when the composites fuselage were considered, at that time it was thought, because fatigue behavior of composite is far superior to the metal. And also in static strength and stiffness terms, it provides higher specific strength. And that is how Boeing and Airbus were able to reduce the pressure altitude to equivalent to 6,000 feet, which increased the differential pressure. Because suppose a cruising altitude, design cruising altitude 43,000 feet, typical, it could be 44, depending upon 42 or 40, but suppose 43,000. So the differential pressure, as you can see from the table, for 6,000 feet is 9.29 psi, considering the cruising altitude of 43,000 feet, and 8,000 feet, 8.43. Okay, now I don't know exactly what was the design condition for 787, whether it was this pressure or what pressure, I can't. Even if I knew, I won't be able to tell exactly unless it's published material. But this is just hypothetical example I've considered, okay? Although it may not be truly hypothetical, of course. But what you see here, I've taken some data. This is from Boeing commercial jet transport, but this is in open literature because it was done under NASA sponsorship, so it's published in NASA report. So, and one would consider, of course, this will be the typical design condition even for 787. It may not be, but most likely it would be the same condition, which this was published by Boeing sometimes in 1980s, which must be the typical design for commercial jet transport. Possible cabin pressure altitude, possibly, I've just said possibly because that report doesn't mention 8,000 feet, because 8,000 feet has been typical for all commercial transport. Normal operating pressure, for which it was designed, that means this is differential pressure they're talking about, delta P to 8.6, which comes out to be fairly close to this calculated 8.43 psi, which is, so that means that's true value almost. So that's so maximum pressure relief. This is another pressure which is considered for the relief pressure. So ultimate pressure only. If the design of the cabin is considered for the structure, Boeing would have considered like 2 into 9.1, so 18.2 psi ultimate load carrying capability, that is pressure, for which the fuselage skin would have been designed, possibly. Now again, let me just tell you, this is not exact condition for 787, but typical example. So ultimate pressure with the flight loads, which is given by this report, is about 13.86 psi, because when you have bending and torsional loads, then they consider, okay, they can reduce the pressure applied for the design, otherwise design becomes pretty heavy. So maximum damage tolerance pressure. Damage tolerance pressure is when they consider, okay, 12-inch crack in any direction, and what is the pressure which should be able to be survived for the residual strength calculation. Okay, so these are the design condition. Now, so considering this is at baseline 8,000 feet, if it is changed to 6,000 feet, that means all these corresponding loads will increase by about 7%. 7% increase, static margins may not, I mean, statically designed may not become too heavy, but fatigue becomes an issue. Even 7% means your life comes down drastically of a structure. And that is why the composite, as you know, the ascent curve is normally flat compared to the aluminum. So it provides you a better life with a composite. And that was the reason how the internal pressure for the cabin could be increased using a composite and is still design lighter fuselage compared to aluminum.
Excuse me, sir.
Yes. Sure.
Sir, good afternoon. This is Franklin here. I'm doing my MTech in aerospace engineering.
Yes.
I've got a doubt, sir. We have told, I mean, it is given in the slide that it is damage tolerant or tolerant to a max of 12 inches crack in any direction, right?
Mhm.
Can we just go to the slide, please?
Yeah.
Yeah, the fuselage skin panel shall be damage tolerant to a 12-inch crack in any direction.
Mhm.
How did this 12-inch become sacrosanct? Because that will depend upon the class of aircraft and the material, right?
Okay, now what happens with the design? This, when I'm talking about damage tolerance diagram, I will explain these things, the various sizes. But the condition for a fuselage design is too big crack. And then load requirement for that is about 70% of limit. That's the damage tolerance design. So those things I'll explain while I'm teaching about the damage tolerance chart, which I would be talking about that behavior. And it's very interesting. And that's one of the most important part of this presentation, the damage tolerance design. So when you was asking me the question, 12-inch in any direction, now normally what happens, 12-inch we consider like a visible damage. And that should be able to be sustained for the limit load carrying capability. Usually that is what I'll explain in my lecture. So it's a visibility of the crack or damage. If I'm talking about this thing, like a visible damage, I'll talk about visible damages like impact damages, what is size, 6-inch hole or 8-inch hole. So those sizes I'll explain. I'll make it more clear in that. Okay?
Okay, sir. Thank you, sir.
But I'll explain you that while talking about damage tolerance. Any other question? Okay, next. It's just explanation. Increased cabin operating pressure induces high fatigue cycling. So static loads using composite, I've already talked about it. Okay. Now, next question was.
Sir, just a second, sir. Can you hear me, sir?
Yeah.
Okay. Is this cabin pressure fixed to a particular value, prefixed, or can it be varied during the flight?
Oh, which one? This pressure?
Yes, cabin pressure.
Oh, cabin pressure, internal pressure is fixed. This is not fixed. What happens? This is differential pressure. Differential pressure we are talking of, the cruising altitude. Suppose there is a design cruising altitude 43,000 feet. But cabin pressure is maintained at 9.29, say, suppose.
Okay.
I don't know what is a Boeing 787 pressure. This is from ICO, basically, the outside pressure, air pressure. They may be maintaining 10 psi or I don't know. But this is a typical value equivalent to 6,000 feet altitude, the air pressure outside atmospheric pressure. Okay. So what happens? The internal pressure is this one. Oh, sorry. I'm sorry. This is differential pressure.
What is the differential pressure?
Internal pressure is this. Okay?
Okay, yes.
Now, outside pressure is 2.49 for this. So at 43,000 feet, this will be the pressure. And you have to design your structure for the maximum operating pressure. We are talking about operating pressure as a differential pressure.
Okay.
Delta P. And that is what, when you are doing say fatigue cycling or structural stresses which are imposed, because there is internal pressure and there's external pressure. So internal pressure is 11.78 psi external pressure is 2.49 psi at 43,000. But suppose it's cruising at 35,000 feet, then differential pressure would be less.
Less, yes.
But because you have to design the aircraft for a highest operating pressure for the structure, that is what you will cycle. Suppose you are doing fatigue cycling of this structure, you would be cycling with this 9.29 psi. Now look at this one. Suppose you are designed for 8,000 feet altitude, your cyclic pressure would be 8.43 psi according to this one.
Yes, yes.
But now you are increasing this. This is about 7% increase, and which reduces the life substantially.
Yes. Okay.
Okay.
Right. Right.
Okay.
But the PI remains constant once it is fixed to a particular altitude pressure. That is the PI, the internal pressure is constant. That will not. It is not variable.
Yes, PI, because what happens, this is our human body, they want to maintain the constant pressure for that.
Yes, yes, okay.
Because otherwise, our body will react, we will feel very uncomfortable if they reduce the pressure inside the cabin. And this is what happens when, suppose, when you are flying in the aircraft, they say due to some reason, if the pressure gets reduced inside the cabin, that automatically those they will have oxygen mass dropping. It is because our body cannot take lower pressures. Due to some crack or something happens in the fuselage, the decompression will occur.
Right.
Another thing which I did not mention last time, in the 787 aircraft, and also same thing happened with 350, because now composite fuselage is being used, they could increase the fuselage, inside the cabin humidity level. And increasing the humidity level inside the cabin also makes our body more comfortable. Now, why it was possible? Because we know composites are less susceptible to corrosion compared to metal. So this was another thing which was introduced during these new aircraft to make the feeling inside the cabin to be more comfortable compared to the previous aircraft.
Right.
Okay, next one. The issue was if you have a different supplier, multiple supplier, you have qualified one supplier, and then how do you re-qualify another supplier, material supplier, alternate supplier? Or it's not only material supplier, another supplier. I've just written down various options. Alternate material supplier, changes in processing site or equipment, changes in raw material supplier, changes in fabric type, style, because somebody says, oh, what happens if the axle or whoever is supplying, they change the stitch type or some changes, then how do you? So again, all those, any minor change or major changes have to be accounted for by us by requalifying the material depending upon the magnitude of the changes, whether it's alternate supplier or material changes or some process changes by the same supplier, some equipment change, assembly line change, any changes. They cannot change anything unless they get approval from the manufacturer, that is customer. So change in binder, alternate material, process divergence by material supplier. So all these things. So next slide. So assess. Well, what happens when the manufacturer of the material or material supplier intends to make some changes? They have to communicate to the customer that these are the changes which you introduce and what is the impact of that. So naturally, as a customer, you try to assess the risk, cost, weight, schedule, certification, impacts. develop required test matrices and test plans. So depending upon the changes incorporated, you have to develop the test matrices. If it's very minor change, a small type test matrix. If it's a major change, maybe large number of tests are required. So depending upon the changes incorporated. So you develop the test matrix depending upon the proposed changes, perform test, and then you have to analyze the data. You may show the equivalency of the changed data with your existing data, whether it has any impact on that allowables. Assess the results. Are allowables affected? Does it impact on design and certification? Impact on cost, schedule, and weight? And then it's your final decision, depending upon the changes and effects. So you have to do all this history. And anyone who is interested in looking at this process, I would refer them to read Mill Handbook 17, Volume 3. Again, I would say it's available from public domain free. And I would recommend each one of you to download all the volumes of Mill Handbook 17. It is a very handy document. Any question on this? Any confusion? The person who asked the question, I don't know the name, but any comments? No. Okay, material selection, of course, we'll discuss today. Then another question was, what's the purpose of full-scale fatigue test? So I thought, let me just highlight a few reasons why fatigue test is required by FAA today. This is damage tolerance. Of course, this is I showed last time the criteria 571B. Current regulations require the full-scale fatigue test of aircraft. And the reason is because why this mandatory requirement was imposed by FAA is after one of the accidents which I'll be talking today about aircraft accidents in history, where a widespread fatigue damage rule, final ruling was provided. What it was, 14 CFR Part 25, 26, 121 Ethel, Aging Airplane Program, Widespread Fatigue Damage Final Rule. This rule, this final rule amends FAA regulations pertaining to certification and operation of transport category airplanes to prevent widespread fatigue damage in those airplanes. For future airplanes, the rule requires all applicants for type certificate after the effective date of the rule to establish limit of validity. I'll explain limit of validity in next slide, the definition. That is basically validity for which the manufacturer is selling the aircraft that this is the life, 50,000 flight, 10,000 flight, or whatever the validity of the aircraft is. Design approval holders and applicants must demonstrate that the airplane will be free from widespread fatigue damage up to the LOV. Now, what is widespread fatigue damage? I'll explain you in these slides. The rule requires that operators of any affected airplane incorporate the LOV into the maintenance program for that airplane. Operators may not fly an airplane beyond its LOV unless an extended LOV is approved. So this is now mandatory LOV. Okay, I've just put some useful references over here. Those of you who are interested in going through this, is a very important criteria for the aircraft industry. And the AC 2107, they're all available from FAA website. You can download this document, very interesting. So 14 CFR AC 2104, which is establishing and implement if validity. Oh, I think I've just missed out this word. Implement little. If validity to prevent, I'll correct it later. Prevent widespread fatigue damage. Then 14 CFR AC 2571D, damage tolerance and fatigue evaluation of the structures. It's a very important advisory circular for the damage tolerance and for the fail-safe structure design. And 14 CFR Part 25, of course, we are talking about that, and Part 26, Part 121. Okay, full-scale fatigue test objectives. Locate areas that may exhibit early fatigue problems. Develop and verify inspection maintenance predictions. Provide test data for analytical service life predictions. Determine the possibility of widespread fatigue damage. This is the major criteria for which NAFA requires the aircraft to be tested for the fatigue. Establishment, because this establishes LOV. Establishment of limit of validity or WFD will not occur in any susceptible area within LOV. What it says, during the LOV or limit of validity which the manufacturer is prescribing life as, the widespread fatigue damage shall not occur. So this is the criteria which needs to be satisfied by the full-scale fatigue test. So this is the objective, essentially. Okay, widespread fatigue damage definitions. Simultaneous presence of fatigue cracks at multiple structural locations that are of sufficient size and density that the structure will no longer meet the residual strength requirements of 25571B, that is FAR regulation. The presence of fatigue cracks at multiple sites of the airplane structure such that the interaction of these cracks degrades the damage tolerance capability of the structure more than any one crack independently. There are two types of WFDs, multiple site damage and multiple element damage. I'll show what it is now. And of course, limit of validity definition, LOV is the operational life in terms of flight or hours of the airplane consistent with the evaluation accomplished and maintenance actions established to prevent WFD. So essentially, what LOV is, as we said earlier, LOV is making sure that there won't be any WFD or widespread fatigue damage. Although the LOV is established based on WFD considerations, it is intended that all maintenance actions required to address fatigue, corrosion, and accidental damage up to the LOV are identified in a structural maintenance program. LOV can be equal to the design service objective. What it means, suppose the life of the aircraft object, design life is 40,000 flights for aircraft. LOV normally, the manufacturer will prescribe equivalent to that life, DSO. And LOV normally is L life without WFD by 2. What it means when you are testing that, that's a requirement that aircraft, when they are fatigue tested, they are tested say to 2 lifetimes. And within those 2 lifetimes, there should be no widespread fatigue damage. And then when you are defining your DSO or LOV will be half of that. Okay, now what is MSD and when we are defining the multi-site damage or multiple element damage? What MSD means, simultaneous development of fatigue cracks at multiple sites in the same structural element. So what we are saying, suppose there is a stiffener to skin joint. Now this joint will have 100 fasteners there. Could be 50, could be more rivets. So there may be some rivets may start cracking, the holes may start cracking, like what you see. And basically, these small damages during fatigue cycle, they would keep on growing and they will merge together. Okay. So these multi-site damages, which are there in one element, after some time they will join and make a large damage, which will be catastrophic to the structure. So what is the objective of WFD? To avoid this happening? And if they grow, they should be picked up before your residual strength drops below the regulatory requirement, the multiple cracks. When we define MED, multiple element damage, now this was within one element only, so one stiffener to skin joint. MED is in different, so you have different stiffeners to skin joints, and they are multiple, so each one, or maybe some of them, so this one will be MSD, this is MSD, this is MSD, but what may happen, gradually the damage becomes large enough and this damage or may join with this one, or probably this also have damage and they may join with this one. And that may be widespread fatigue damage due to multi-elements. So damage in the groin, yeah.
These MSD and MED, are they specific to metallic structure or are they relevant to composites also?
Good question. These definitions came from metallic structure, essentially when the metal structures were failing. Such damages, of course, today in composite structure may not occur.
Yes, that's what I thought. Okay.
Yeah, you are perfectly right. But what happens, these rules came from metallic structure failures, and composites are still very new. But when we are talking of fatigue life of a structure, whether it's a composite or metal, currently the requirement is same. Even though for composite, this may be a hypothetical scenario. It may happen, but really the composite damages don't grow because we are designing with the criteria of no damage growth.
Okay.
Unlike metals.
Okay.
So you are fine, yes, but these
Right.
pictures are from metallic structure.
Okay. Okay.
Okay. So now I've already explained, and this is some pictures I'm showing here. So multi-site damage, essentially with an element, and maximum allowable damage connection up to a size load related, no significant damage beyond this region. All MSD within this area is local and already accounted for. So essentially same. I think I won't repeat this. I've just shown the diagram. Okay, so this should be clear now why the fatigue test of aircraft is required by FAA, and I would provide some more background about this one when I talk after this. Question answers the historical failures in aircraft. Okay, next one. Do we need to test the derivative aircraft as full-scale fatigue test? Now the question was, somebody asked, okay, do we test every aircraft? No, I said clearly, no, that's not possible. It's only the one designed aircraft which is tested for that version. So now the question is, say 787 has got 3 versions today. 787-8, -9, and -10. The baseline was 787-8. The fatigue test of whole aircraft was done with the -8. So the question is, what happens to the dash 9 and dash 10? Or similar to the Airbus when they have different derivatives. Now, those derivatives which are there, they have increased sizes. However, you are always piggybacking on the baseline aircraft because there are no major changes. Still, for a derivative, LOV is again defined based on WFD criteria. Criteria remains same. The only thing is, how do you certify that derivative? Now, based on your analysis and testing, which you have done for the original version of the aircraft, you can extend the principles of the analysis and negotiate with FAA or European or regulators and avoid testing the whole component again. It may be possible that you may test locally subcomponent part of it and try to demonstrate the equivalence and do not have to test the derivative again. Okay, now point design question. Another thing was why point design expensive in the long run? Oh, spelling error here, I'll correct it. Okay, now I just draw a flow diagram for the limited. What happens with the point design? Company wants to save, suppose, the money initially and time. They would do some limited allowables data just to do the design, and then they will manufacture the full scale component and test it. So essentially the testing is done by, the certification is based on the whole of the component testing. The downside of this is it has a limited allowables test data. It doesn't have all various elements, sub-elements, subcomponents test data available, which will ensure that you have been able to determine if there are some unknown effects, some surprises. So lack of understanding of various design and processing issues, and that is what will happen. You may not be able to understand if there are certain issues earlier, because when you are testing the full component, it may be too expensive if you realize there are some deficiencies in the process or the structural design, the changes become more expensive. So discovering the flaws or technical issues later may become expensive and may lead to weight penalty. Any modification to design, process, materials, future derivatives will require the full scale test again. And so that means suppose Boeing would have tested, which is basically certified 787-8 based on point design. When they designed 787-9-10, they would have to test whole of the aircraft again, every version, which may become too expensive. And what happens when you want to change some design concept or make some small changes in the design? If you have not developed your analysis methods and verified by test and done lots of subcomponents, it becomes very difficult to make the changes, howsoever minor it may be, without redoing whole of the test. And that is why the point design approach is not used by these major industries, because in long run, it is more expensive. Did I make it clear now to those who were confused about point design approach?
Yes, sir.
Okay. Okay, so this finishes, unless there are some more questions from the previous presentation. Now, okay, I'll take up okay, now we talked about the certification process, and I showed some slides providing the definitions of various terms for the certification, and we discussed this design certification approaches and certification analysis by test. And then I did show the building block approach diagram, but I've just changed the order of those slides. And the material is, you can just download again. I've sent the revised presentation today to Professor Dinesh, who would have put in on the server to be shared by everybody. Okay, now, so this is, I just want to talk about this one, although this shows. So why the certification is done? What is the objective? So final objective of certification of any product is, by the regulators, is to ensure safety. Design, fabrication, operation, maintenance. So the main objective of all this exercise is to ensure the safety of the people, passengers, on ground, everybody. So safety, safety, safety. This is very much highlighted in the aircraft industry at every step. We cannot cut corners. After working in aircraft industry, I realized how important it is to maintain safety within workplace, the design, fabrication at every level. We have to consider safety. Okay, now let me talk about the historical failures, because it's very important to understand what has happened during this history of the regulations, which led us to learn from the failures. That always happens.
Hello.
If there are no, yes.
Sir, are you presenting any slide? Because we cannot see.
Oh, is it? How come?
Yeah, your cursor is moving.
Can you see now? No?
Yes.
So it's okay. Okay. So actually, this one probably you might have missed the final objective of certification. This is a slide, which that's it. Okay, now what I want you to talk for some time about historical failures and the regulation changes, learning from the history. And it's very important, actually, you being aerospace engineers, and you may be joining after your graduation, doing some research, joining the industry or academic. But it's a good idea to just scan through the history about these regulations changes, what we have learned out of it. Okay. This diagram is quite important, and there's a lot of message in this diagram. This I have taken from FAA website based on Fuselage Structural Integrity Forum about the FAA accidents. There have been some classical failures which changed the direction of the certification.
Dr. Garg,
Yes.
I am still seeing the single slide certification philosophy of composite aircraft question and answers. I am not seeing any change here. Are others able to see the change in slides?
No, it's still on the first slide.
No.
Maybe you can unshare and reshare, Dr. Garg.
Oh, I see. Maybe let me just go to the team and then see what has happened. Why is
We still have your old presentation opened, the responses to the questions from the previous session.
Well, let me see why this share more actions. Show background if you know.
Because there are multiple share options. One is to share just the presentation. The other is to share your screen.
Okay, let me just see now.
Shared the
Open.
old presentation.
Well, it says open share tray actually, because I know there used to be option for share a screen.
Right.
But yes, let me just, okay.
Yeah, you can make it full screen as well. Yeah, thanks. Now it's fine.
Okay. So essentially, so when I started the safety, this slide, but then historical failures and regulations changes, learning from failures. Okay. This slide which you see, it is a good slide telling a lot about the regulations changes and why it happened. What you see, the first one, in 1950s, you know, the first commercial jet liner, airliner, the Comet, was designed in 40s and the beginning of 1950s, it started flying. It was a beautiful aircraft. Unfortunately, 3 aircraft failed in early 1950s. I think 53, 54, within 1 year, 3 aircraft failed. And that led to lots of investigations, what had happened. When comets were designed, the design philosophy was the safe life of the structure. And we'll talk about safe life, what safe life means. And which may not have been able to pick up the deficiencies in the design. And after that, failure investigations, then FAA, which used to be basically civil aviation regulation, this car is nothing but present FAA. So, which is FARs now. So amendment B270 was issued on March 13, 1956 of this Comet's investigations. And then from safe life, the criteria became to fail safe. And again, I'll explain what the fail safe criteria is. It's quite important to understand these philosophies. So even with the fail safe design philosophy, in 1977, Boeing aircraft failed. And we'll talk in the further slides. I've just explained what are the reasons for that. So that means the fail-safe characteristic is still failed to predict the realistic life of the aircraft. And then Amendment 45 was issued by FAA in 1978. They changed the design philosophy from the fail-safe to damage tolerance. In damage tolerance, you have to consider some initial defect, assume the initial defect, and then determine the life of the aircraft structure. And that is the current philosophy, mandatory damage tolerance. Okay, now, and then what happened? Even with all these criteria, now damage tolerance and fatigue, what you see here, the 2 lines, the green line is still continuing the safe life. Now, the criteria is there are still some structures which are based on safe life design, landing gear struts, rotor blades. However, the caveat is if the structure the inspection is not possible, then you can design with a safe life philosophy. Otherwise, the damage tolerance philosophy. Now let's look at JAL accident. What happened in 1985? Japan Airlines. This is the worst disaster in aviation history. Japan Airlines, about 525 people died. Then another accident in 1988, Aloha. What happened because of this accident? This accident led to Amendment 96, which we talked about WFD. Remember, a couple of minutes back, widespread fatigue damage. This came after Aloha accident. And this is, as you can see this line here, full-scale fatigue test. I mean, designs, aircraft manufacturers were doing the full-scale fatigue test even prior to that, but it was not mandatory. This became mandatory only here. And I will explain you later on from the further slides. Because of JAL accident, then this modification, FAR 26 came into picture. This is repair damage tolerance. I'll just explain it. AC 2073 in 2000. So what you see from this diagram, some of these classical accidents or failures change the direction of that certification. Okay, let's talk a bit on this detail.
Hello.
Yeah. Yes.
So in the previous slide, if I'm not wrong, if the inspection is possible, then we go for safe life design, right?
Inspection possible, then damage
safe
tolerance.
Life. Okay.
The inspection
And
not possible. This is no.
Okay.
If it is no, then only safe life, which is
Okay.
only for a few components like landing gear strut.
In that inspection is not possible.
Well, it's difficult. Those steels and normally they are designed with a safe life philosophy.
Okay.
All the structures where the inspection is possible, that's mandatory that you have to design with damage tolerance approach.
Yes, sir. Thank you, sir.
Okay, now, how could the Havilland? In fact, basically, how could this Comet failures led to the, drop in the business of aviation in UK? So BSC flight 781, location Elba Island off Italian coast, January 10, 54, all this. The failure of cabin structure owing to metal fatigue. I don't have time to go through the video, but I would recommend you to look these failures in YouTube. Links are given here. Aircraft. It's very interesting to watch the video of these failures to understand what went wrong. They're beautiful videos. Okay, the issue was with this, with one of the Comet failures here after investigations. I've taken the picture from the failure investigations, what you see here, the cracks around the window. There is square window. The square window, high stress concentration, as you would know, in the corners. Normally, you would not like to design the window with a square. Of course, none of the windows after this are ever square. They're always elliptic. But this is what happened. The cracks initiated from the corners in fatigue and led to the failures, disastrous failures, which Hockaday Havilland didn't realize when they designed this. They, in fact, had proof tested it twice the design pressure and approved the design. Okay, this just shows comet failures cause good design, elliptic hole, we know that. This is a poor design. Okay, the issue, what you see in this diagram, and so in the left, it shows the initial cycling of 30 cycle of the aircraft cabin under this pressure. P is 8.25 psi per cycle, that is operating pressure, for which it was tested. So they applied double of this pressure, that means 16.5 psi pressure for 30 cycles, and then they applied the failure occurred after 18,000 cycles. So that means the total number of cycles, life of this cabin or fuselage is about 18,000 cycles, 18,030 cycles that way. However, look at the right. When they tested the cabin with the operating pressure of 8.25 psi, they got only 3,557 cycles. What is the difference? Why this is there? Anyone from the audience? The cause. Why in one case?
Defects.
Yeah. Pardon?
Defects.
No.
High cycle fatigue and low cycle fatigue.
Yes, that is the reason. What happens, as you would understand, in fatigue, this causes the overloading effect, and this causes cold working of the region. And that cold working causes the plasticity effect, causes the deceleration of the crack propagation, and increases the life. Whereas in this one, there is no overloading phenomena, no cold working. So really the life is much less. And this phenomena was never understood by Havilland at that time. The fatigue. Because fracture mechanics was never used before that. It came much later on. And this overloading effects were not assessed. Lack of understanding of metal fatigue. And that was the reason. And that is why the aircraft comet failures occurred much before their design life. Okay. Next one, Danair.
Excuse me, sir.
Yes.
Sir, I have a doubt. Like here, the pressure is 8.25 psi, no, sir. While testing, how actually this pressure will be created? Because in actual condition, this is the differential pressure. While testing, how this differential pressure will be achieved?
Well, they would always they can have the pressurized cabin. So they would be applying the pressure during testing, internal pressure. So that is how they will create a differential pressure. You have external pressure, room pressure, and then you have to increase the pressure inside the cabin. And that is how the differential pressure will be created.
Okay, sir. Got it. Thank you, sir.
Yeah. Okay, then here, this was Boeing model 707. Now, as he said, at this time, the fail-safe philosophy was there. When Comet was designed, the failure occurred at that time, safe life philosophy. Here, fail-safe. So this aircraft had been designed using the fail-safe philosophy, and still there was a failure. Fracture of right hand is horizontal stabilizer, no survivor. Investigation led to the fractured stabilizer revealed that the fail-safe characteristic of the structure did not perform as intended. Shortcomings in design assessment, certification, and inspection procedures. Again, you can watch the accident, the failure on YouTube. Interesting video. So the failure, this is the failure. Horizontal tail rear spar failure. Rear spar, which almost was taking 80% of the bending load. And this has the top chord, top web, center chord, lower chord, lower web. So the spar web flange is divided into these sections in order to have the fail safety measures. But still, it failed due to the overloading. Okay, now here I've just taken a picture from the same. This is a Denier failure. What happened? This aircraft, before Denier took it, it was with Pan Am. Pan Am had served for 16,285 landings. And during this time only, it seems, the fatigue cracks had already started growing, which are not determined. They were not found by the inspection, it seems. So fatigue crack. And then there was a sudden jump. At this stage, it's a Denier tenure, which failed within 438,000, but it had already done 16,000 flights and another 400 flights. So major static jump is short static jump, and then the final static failure, and that led to the total failure. So it's essentially due to the development of the fatigue cracks. And if those cracks are not able to be picked up during inspection, they may become catastrophic. And that is why the damage tolerance approach is far more reliable than the fail-safe. So today, it's a damage tolerance criteria, which is almost mandatory. Okay, so damage tolerance evaluation, this led to the damage tolerance. The evaluation must include determination of the probable locations and modes of damage due to fatigue, corrosion, or accidental damage. Repeated load and static analysis supported by test evidence, and if available service experience must also be incorporated in the evaluation. Okay. Third accident, which led to widespread fatigue damage. Criteria, final loading. Aloha Airlines Flight 243, location of failure Hawaii, April 28, 1988, Boeing model 737-297, and the failure was damage to fuselage after an explosion, decompression. Investigation led to the failure of Aloha Airlines maintenance program, because during maintenance program, they could not pick up the damage which was already propagating. Detect the presence of significant disbonding and fatigue damage, which ultimately led to the failure of lap jointed stringer S10L and separation of the fuselage upper top. So if some damage is not able to be picked up during inspection, it may create havoc. So this led to the issuance of Amendment 96 for widespread fatigue damage. So when we were talking about fatigue damage, it was because of this criteria, this failure FAA made a ruling on widespread fatigue damage ruling. And that's why now the LOV or limit of validity of the aircraft is defined, which will ensure by test and analysis that there won't be any widespread fatigue damage causing the failure of the aircraft. You can see here the failure, total separation and loss of major portion of upper crown skin and other fuselage structure. Okay, now what happened during this accident? Why it happened? And you can realize the importance of any joints. Essentially, most of the aircraft accidents have occurred due to the joints failure. Normally, the cracks start from the holes, rivet holes or fasteners, or the cracks in the rivet or the fasteners. They lead to the failures. In this case, this is outer upper skin and this is lower skin joined with the bonding and the rivets. This bonding was done as a cold bonded lap joint rather than the hot bonded. Of course, now currently the practice is to use a hot bond because cold bonding is not that strong enough and durable. So you wouldn't design a joint with a cold bond these days. But at that time when this aircraft was made, at that time Boeing probably was using this practice of cold bondage. Okay, now what happened? During service, due to fatigue, bond line broke. Imagine situation now, what happens when bond line is intact? The rivets will not be loaded at all because bond line will take all the load. Joint stiffness is higher and this rivets will not be acting virtually. But when the bond line failed during service, what happens now? The rivets start loading. Unfortunately, the rivets are not capable of handling high loads, it seems. They are knife edging on the skin. And due to this knife edging, as I've shown in this presented diagram, the cracks started. These cracks increased, multiplied, a widespread fatigue damage was created, and that led to the failure. So failure events, failure of bond line between upper and lower skin splices. This bond, load gets transferred to the rivets. Rivet side knife edged or upper skin. Increased stress concentration around rivet holes, leading to crack initiation and thus splice joint failure, causing upper and lower skins to separate. The further design was improved by hot bonded adhesive. Okay, so this is now another accident. This is the most catastrophic accident or crash in the history of aviation, where 521 passengers died. And in addition to this, after the accident, it seems the general manager of Japan Airlines maintenance program committed suicide. And this was again a Boeing aircraft, of course. Investigations, the root cause of the explosive decompression was attributed to an improperly executed repair of the airplane's aft pressure bulkhead that was completed several years prior to the accident. If during maintenance, the worker commits a mistake, that could be very expensive. And this is what happened. I'll show you next slide what happened during the repair. Prior to that, there was no damage tolerance requirement for the repairs. But after this Japan Airlines accident, as I showed in that diagram, repairs damage tolerance is mandatory now. So when we are designing the repairs, we have to consider the failed repair condition. It is a must. Because you have to design the structure that if the repair fails, still it doesn't become catastrophic. And we'll talk about that when I'm talking about details later on. Okay, so let's just consider now what happened during this here. Whole of this part, rear part got separated. It's very interesting, actually. Again, I would emphasize, just in your leisure time, go to YouTube, watch this video. It's very interesting to watch Japan Airlines crash video. On the left, there's a correct repair. On the right, actual repair joint. Now what happened here, you see the design for this upper dome, lower dome is can, and there's a splice plate, rivets, the stiffener. So this is continuous. All this splice plate is continuous. Whereas, because this repair was difficult, it seems to be performed during maintenance. So maintenance personnel, without understanding the implications, cut the corners, they cut the splice plate here to simplify the repair. So what's the consequence of this? Yeah. Earlier in this case, when the load is being transferred, you know, there are three rivets which take the load. Of course, this will take the highest load, first rivet. But suppose this takes around 35%, and this takes about 30%, say. But in metals, normally, at ultimate load, the loads get equally distributed. When we talk of the unequal load distribution, we talk in composites because they don't yield. And that I'll talk in the joint design, the load distributions. So here you see these three, all the three rivets are acting to share the load. When this splice plate is cut, what happens now? This rivet doesn't take any load. It's just cut off from the load path. So that means the load is directly dumped to this rivet. So instead of three rivets acting, now it's mainly one rivet taking the load, directly supplying the load to this, most of the load. And then what happened, because the rivet is overloaded, it causes the initiation of cracks, which propagate, keep on joining, and lead to the failure. You see this slide where so the cracks initiated, some crack would initiate and then continuously they kept on growing. So improper repair led to the fastener overloading resulting in cracks. Over time period, 7 years between the repair and the accident, fatigue cracks propagated along the row of fasteners, leading to rapid fracture. So essentially, this is like a widespread fatigue damage, gradually propagated and led to the failure. So lessons learned, repairs should be accomplished in a manner that preserves the original safety features of the airplane. Aircraft maintenance programs should be developed consistent with actual aircraft operations. Fatigue properties of complex structural elements should be well understood so that in-service maintenance programs are properly designed. And this led to, as I said, issuance of AC 12073, which calls for the repairs damage tolerance. Any comments, any questions? In fact, it's only 10 minutes left in the lecture, and let's see if there are some questions.
Yeah, I have a question.
Yes.
Yeah, now the slides you were showing a cold bonded adhesive.
Yes.
When it was converted, when it was improved to hot bonded one, the situation improved. What sort of laboratory tests you do to compare the cold bonded and hot bonded, either at the specimen level or a part structural level or the entire component level? What sort of testing to prove that with confidence that it's because of this?
Well, I'm not sure what testing would have been done by Boeing at that time, and it's very difficult to go into the history. They would have done lots of investigations.
Fine.
They would have tested the coupons, they would have tested the elements, and redesigned the components or subcomponents. However, your question regarding how do you make sure the hot bonded and cold bonded differences? So the best thing is you would do some testing using the like lap shear coupons.
Yeah, that's
so
what
these
one
days,
expects. That's what one expects. Possibly a part structure of that element, some load test relevant to the design also must have been a possible
they would have done that. That is an element test, because let me tell you, Boeing normally takes the things very seriously, and lots of testing before they put anything. They would do a lot of testing, so they would have done enough testing to substantiate the bonding. They would have revised, although this is only one parasite here, further improved by bonding. I do not know what was the improvement done. It's very difficult.
Thank you.
Okay.
Yeah.
Now, coming back to your question regarding this bonded joint.
Yeah.
These days, normally, we use the fracture mechanics approach. So if I have to design a joint, I would test for G1C, G2C, that is fracture toughness or delamination fracture toughness in mode 1, mode 2. We do not rely on the joints design using the strength approach today. That is our basic philosophy. We use only the fracture mechanics approach. For now, everything, wherever this, and I'll talk about that actually when I'm talking about the laminate design, the radius. A few places I will talk about the fracture mechanics approach. So coming back to this, your question, suppose you want to understand the difference between hot bonded and cold bonded. One of the basic specimens of core lap shear test. The second thing you will do, which is more reliable, use G1C and G2C test, the delamination mode 1, mode 2. And we can talk about it later on. Is that?
Yeah, okay? It's fine. Sure. Yeah.
Okay. Any other question?
Excuse me, sir.
Yes.
Sir, between this safe life and fail-safe design, out of these two approaches, which one overestimates the life of the material or something like that? Because this is dependent on number of cycles, right?
Yes. In fact, I'll talk about that. Now, if you see here in my further presentation, we'll be talking about the the differences in safe life and fail-safe damage tolerance. To provide exact answer to that, it's difficult which one is higher in life. Okay,
Okay, sir.
So after this accident investigations, I can maybe I think I may start in the next lecture, but if you have any more questions, I'm willing to answer.
Yeah, Dr. Garg?
Yes.
Yeah, where the whole set of slides in presented today, very interesting and very informative. But all these are referring to the metallic structure, I guess. All these accidents, all these cases were purely metallic, I guess. Maybe it evolves into composite structure. Perhaps this information is what I think. Is it so?
Okay. Now, it's a good question. Why I try to show this, the philosophy, say, composite structures, they follow this. Why I wanted to show these accidents are important part in the science. They tell us why we use the philosophy of damage tolerance or fail safe or safe life. What are the differences? Why today damage tolerance approach is mandatory? And I understand all these accidents occur due to metallic structure, but they have taught us a lot. Still, 50% of aircraft is metal.
Yes.
I understand our objective is to talk about the composite structure design philosophy here. And if you see all the presentation which I have now further, it's all composites now.
Right. That's fine. I just yeah.
So I'm not deviating from the focus of composites because that's the main topic. However, the philosophy for composite and metals are similar, with the additional requirement of the composite structures. All this, if you scan through my lecture, you will find everything is composite beyond this criteria. No matter.
That's fine, Dr. Garg. Even otherwise, it was very interesting, and I'm sure all this information and analysis would have helped to arrive at the analysis of composites and all that.
Yes, that's right. But if you see this diagram, damage tolerance diagram, which I'll be talking, and this is the main diagram for all the design, whether it's a metal or composite, this diagram doesn't change. Essentially, this is of course for composite, but the residual strength requirement is same. We don't talk about visible, undetectable damage, detectable damage. This is of course for a composite, but it's a damage tolerance philosophy.
Right, sir. Thank you.
So we'll discuss more in detail next week, although, of course, I've been going pretty slow, it seems. I may have to go a little bit faster in order to finish this.
So thank you very much, Dr. Garg. I think it's okay to go slow so that you answer the questions to the satisfaction of all the audience members. So I think that's more important. So if necessary, we can probably extend it by a day or two, depending on your availability.
That's fine with me, actually. And yeah. This happened with Ada also. Actually, this lectures kept on extending. I really liked it. It doesn't matter for me.
Yeah, because I think
like to go slow because I want.
When you cater to the questions of the audience, many of which are highly relevant. So, and you're putting in a lot of effort towards answering that. So I think it's going pretty well.
That's okay. I'm happy to go with this, slow pace, because the objective is to understand things rather than going fast and finishing the slides. That doesn't serve much purpose. Right. But I would like, these are all useful things. Each of the criteria and each of the, actually most of the slides which you'll find are very relevant, and especially for the people who are thinking of joining the industry, where they say ADA or HAL, anywhere or outside India, or doing the research. Important topics actually out of this one for even PhD students.
Yes, Dr. Prag, I fully agree with Professor Dinesh. I think we are comfortable at this pace, and this is very valuable information, not very easily available otherwise. I think we are comfortable with this.
Okay, that's good to hear.
Sir, the additional slides which you put today, catering to question and answers, also will be uploaded, I guess. There were
yes, Dr. Bhatt, I have already uploaded that.
Okay,
so it's available on the both the SharePoint as well as the Teams files.
Okay, great. Good.
So this is what I'll be doing, these questions, answers when you are asking me. And I'll try to elaborate the answers and add the questions and answers in the same presentation every week.
Right, sir. Thank you.
I have a question.
Yes, please.
Sir, suppose if a crack has reached a critical length, can we do any design modification so that that crack length is further arrested from growing further? I mean, the propagation is arrested from growing.
Yes, the crack arrest phenomena that you have to design it so that the cracks don't propagate further. Like suppose in composite structure, the requirement is when you are trying to determine the residual strength, suppose the wing skin is stiffened structure. So the requirement is a two-bay crack. You have to design that. Beyond two-bay crack, the crack should be arrested. The residual strength should not drop below the regulatory requirement. And we'll talk about that. If you see, in fact, in this presentation, I've got the slide. See this one, and we'll talk about that.
Okay, sir. Thank you.
Most of the things are covered in this, what you need for the certification of a composite structure. Almost I have tried to cover each of the phenomena which you need to satisfy, each of the criteria for certification of the structure. So you can just scan through this presentation. You have already got a copy of it and see. In fact, you can you can ask the questions based on this presentation in the next lecture. I may clarify more the contents of the slides. So I've tried to cover most of the things, as you will see in this.
Sir, shall I ask one more?
Yes, sure.
Sir, I have read like in composite structures, they offer very low sound attenuation compared to the metallic structures. So does the use of composites in aircrafts call for a higher cabin noise, or how is it tackled from the human comfort point of view regarding certification?
Okay, now I'll show you that. We talk about sonic fatigue. Bird strike. Okay, sonic fatigue. I'll cover it.
Okay, sir, fine.
Here I put some explanation. Although I have not been able to go into the details, but each of the subject is a big subject.
Excuse me, sir.
Yes.
So just one last route. Sir,
sure.
and there's fasteners, we have this knife edge where the stress concentration is very high. So how are we going to eliminate that, or are there some efficient fasteners where this knife edge is less? Like, because rivets are used almost in all the parts to connect. So are we using something like how do I say that? Like
in composites, we don't use
fillet. No, not in composites. In metallic structure, like I was thinking.
Yes, in metallics you have the rivets, but again there's always a rivet to skin thickness, rivet diameter to skin thickness appropriately considered so that you don't have that knife edging, the cracks initiating easily. So there's always a minimum thickness to the rivet diameter. So the countersink is not as deep to cover and provide you significant amount of knife edging so that the cracks initiate.
Okay, sir. Thank you.
So there's always a requirement for that. I could try to put some requirement next time. Any other question?
Probably. Yeah. Is there any other question? Okay, I guess there are none. So Dr. Garg, thank you once again. Good night, and we'll meet you on Monday next, again at 3 p.m. Indian Standard. Yeah.
So good evening. Good evening for all of you, and it has been very pleasant for me to have shared many thoughts, and I really enjoyed the questions being asked from the students. Good. Okay. Good evening.
Bye-bye.
Bye.
Thank you, sir.